Welcome to this rigorous scientific lecture on giant magnetoresistance, or GMR. We'll explore how this quantum mechanical phenomenon in layered nanostructures became a revolutionary device principle that changed data storage forever. In the late 1980s, Albert Fert and Peter Grünberg independently discovered that the electrical resistance of thin magnetic multilayer films changed dramatically when exposed to an external magnetic field. This discovery would earn them the Nobel Prize in Physics in 2007. The word giant is crucial here. Normal magnetoresistance effects in bulk materials show resistance changes of less than 1%. But in these carefully engineered nanostructures, resistance changes of 10 to 50% or more were observed. Let's begin with the experimental workflow. Step 1 is measuring resistance as a function of applied magnetic field. This is the foundational measurement that reveals the GMR effect. Here's our experimental setup. We have a thin film sample consisting of alternating magnetic and non-magnetic layers. Red represents ferromagnetic layers like iron or cobalt. Blue represents non-magnetic spacers like copper or chromium. We pass a constant current through the structure and measure the voltage drop as we sweep the external magnetic field. The key observation is this. As we increase the magnetic field from zero, the resistance drops dramatically. In the best samples, we see resistance changes of 10 to 80%. This is orders of magnitude larger than conventional magnetoresistance. This is a typical GMR curve. At zero field or low fields, the resistance is high. This corresponds to antiparallel alignment of magnetic layers. As the field increases beyond a critical value, the resistance drops sharply to a low value. This corresponds to parallel alignment. The resistance change can exceed 50% in optimized structures. Now let's ask ourselves a fundamental question. Why does the relative alignment of magnetic layers affect electrical resistance so dramatically? The answer lies in spin-dependent electron scattering. To understand the effect, we first build a baseline model that ignores spin-dependent scattering. This classical model gives us a reference point to appreciate the quantum mechanical enhancement. In the classical Drude model, electrical resistance arises from electrons scattering off lattice imperfections, phonons, and impurities. The resistivity is inversely proportional to the mean free path and electron density. The resistivity ρ equals m over ne squared tau, where m is electron mass, n is electron density, e is electron charge, and tau is the scattering time. For a multilayer stack, in the simplest approximation, the total resistance is just the sum of resistances from each layer. This assumes current flows perpendicular to the layers, which is called CPP geometry for current perpendicular to plane. R total equals R1 plus R2 plus ... plus Rn. The key prediction of this baseline model is that resistance should not depend on the relative magnetic alignment of the layers. Magnetism doesn't enter the classical picture in any significant way. But experiments clearly show that resistance depends strongly on magnetic configuration. This tells us that our baseline model is missing a crucial ingredient, electron spin. Step 3 in our workflow is fabricating controlled layer stacks with precise thickness and interface quality. This is where nanotechnology becomes essential. The most common fabrication techniques are molecular beam epitaxy, or MBE, and magnetron sputtering. These allow atomic layer precision in depositing materials. Here's a schematic of the fabrication process. We start with a substrate, typically silicon or glass. Using MBE, or sputtering, we deposit layers one atomic plane at a time. Red layers are ferromagnetic materials like iron, cobalt, or permalloy. Blue layers are non-magnetic spacers, like copper or chromium, typically 1 to 3 nanometers thick. The critical parameters are layer thickness, which must be controlled to within a few angstroms, and interface roughness, which must be minimized. Even one monolayer of roughness can reduce the GMR effect significantly. A typical GMR structure might consist of iron layers 2 nanometers thick, chromium spacers 1 nanometer thick, repeated 20 to 50 times. The total stack thickness is only about 100 nanometers. Let's do a quick back-of-the-envelope calculation. How many atomic layers correspond to 2 nanometers of iron? The lattice constant of iron is about 0.25 nanometers, so one atomic layer is about 2.5 angstroms. Therefore, 2 nanometers corresponds to about 8 atomic layers. This shows we're working at truly atomic scales, where quantum effects dominate. Step 4 is systematically comparing the resistance in parallel versus antiparallel magnetic configurations. This is where we see the GMR effect most clearly. Here's the key insight. On the left, we have the parallel configuration, where all magnetic moments point in the same direction, achieved by applying a strong external field. On the right, the antiparallel configuration, where adjacent layers have opposite magnetization, which occurs at zero field in certain structures. The resistance differs by a huge factor between these two states. We define the magnetoresistance ratio as a quantitative measure of the effect. MR equals R antiparallel minus R parallel divided by R parallel times 100%. Let's work through a concrete example. Suppose we measure R antiparallel as 100 ohms and R parallel as 60 ohms. Then MR equals 100 minus 60 divided by 60 times 100%, which equals 67%. This is a giant effect. So what microscopic mechanism causes this enormous difference in resistance? The answer is spin-dependent scattering at interfaces and within the layers. Step 5 is developing and fitting a quantitative spin transport model. This is where the physics becomes beautifully precise. The fundamental concept is that conduction electrons, with spin up and spin down, form two essentially independent conduction channels. We can think of them as two parallel resistor networks. This is called Mott's two-current model, proposed by Neville Mott in the 1930s, but only fully validated with GMR experiments. Here's the circuit analogy. Spin-up electrons form one channel with resistance R up, and spin-down electrons form another channel with resistance R down. These two channels are in parallel, so the total resistance follows the parallel resistor rule. 1 over R total equals 1 over R up plus 1 over R down. In the parallel magnetic configuration, majority spin electrons have low scattering because they see aligned magnetic moments everywhere. Minority spins scatter strongly, but the low-resistance majority channel dominates. In the antiparallel configuration, both spin channels encounter alternating layers where they are majority then minority. Both channels scatter strongly, roughly half the time. The overall resistance is much higher. To make this quantitative, we introduce a spin asymmetry parameter beta, which measures how differently majority and minority spins scatter. Beta equals rho down minus rho up, divided by rho down plus rho up, where rho down and rho up are the resistivities for minority and majority spins. For strong ferromagnets like cobalt or iron, beta can range from 0.4 to 0.7. This means minority spin electrons experience 3 to 10 times more scattering than majority spins. The GMR ratio can be expressed in terms of beta through a relatively simple formula in the limit of many layers. MR is approximately beta squared divided by 1 minus beta squared. Let's calculate. If beta equals 0.5, then beta squared is 0.25. MR equals 0.25 divided by 0.75, which equals 0.33 or 33%. This matches experimental observations quite well. The fitting procedure is straightforward. We measure the GMR ratio from our resistance versus field curves, then invert the formula to extract beta. This tells us the degree of spin asymmetry in our materials. Step 6 is the critical validation step. A good model must predict how GMR scales with structural parameters like layer thickness and interface quality. This is where theory meets engineering. Prediction 1. GMR magnitude should oscillate and generally decrease as the non-magnetic spacer layer gets thicker. This happens because the coupling between magnetic layers weakens with distance. This graph shows the oscillatory decay. The oscillations arise from RK-KY coupling, which is a quantum mechanical interaction mediated by conduction electrons in the spacer. The period is related to the Fermi wavelength. Prediction 2. GMR should increase with the number of repeating bilayers, then saturate. This is because more interfaces mean more spin-dependent scattering events. However, it saturates because electrons can only maintain their spin orientation over a finite distance called the spin diffusion length, typically 10 to 100 nanometers. The spin diffusion length lambda SF equals the square root of d times tau SF, where d is the diffusion constant and tau SF is the spin flip time. Prediction 3. Interface roughness should degrade GMR severely. Even 1 or 2 monolayers of roughness can scatter electrons and flip spins, reducing the effect. Experimentally, all 3 predictions have been beautifully confirmed. By systematically varying layer thicknesses, number of repeats, and growth conditions to control roughness, researchers have validated the spin transport model in exquisite detail. Let's look at a specific example, iron-chromium multilayers, which were among the first systems to show GMR. At a chromium thickness of 0.9 nanometers, there is strong antiferromagnetic coupling. The layers naturally align antiparallel at zero field, giving high resistance. At 1.8 nanometers, the coupling switches to ferromagnetic due to RKKY oscillations. Now the layers align parallel at zero field, and GMR is small. At 2.7 nanometers, it switches back to antiferromagnetic, and GMR reappears. This oscillation with period roughly 1 nanometer matches the RKKY theory perfectly. Now let's discuss how GMR became a transformative device technology, revolutionizing data storage in hard disk drives. Here's how it works. A GMR sensor, only a few nanometers thick, flies just a few nanometers above a spinning magnetic disk. The disk contains microscopic magnetic domains representing bits of data. As different bits pass under the sensor, the stray magnetic field from each bit switches the sensor between high and low resistance states. When a 0 bit passes underneath, its magnetic field aligns the sensor layers parallel, giving low resistance and a low voltage signal. When a 1 bit passes, its opposite field creates antiparallel alignment, giving high resistance and a high voltage signal. The large resistance change, 50% or more, provides an excellent signal-to-noise ratio. This enabled bit densities to increase by more than a factor of 100 since GMR was introduced in 1997. Before GMR, hard drive areal densities were around 1 to 2 gigabits per square inch. With GMR sensors, densities reached 100 gigabits per square inch by 2005 and have continued to grow. For practical devices, a structure called a spin valve was developed. This optimizes the GMR effect for sensor applications. A spin valve consists of a pinned magnetic layer whose magnetization is fixed in one direction, a thin copper spacer, and a free layer whose magnetization can rotate in response to small external fields. Only the free layer responds to the weak stray fields from disk bits, while the pinned layer provides a reference direction. The pinning is achieved by depositing an antiferromagnetic layer adjacent to the pinned layer. This creates exchange bias, a strong interfacial coupling that requires large fields to overcome, typically hundreds of Oersteds. Let me briefly mention some advanced topics in current research directions building on GMR. Tunnel magnetoresistance, or TMR, uses an insulating barrier instead of a metallic spacer. Electrons tunnel quantum mechanically through the barrier. TMR can reach 300% or higher, even larger than GMR. Spin transfer torque is a phenomenon where a spin-polarized current can exert a torque on and switch the magnetization of a magnetic layer. This enables magnetic random access memory, or MRAM. The broader field of Spintronics aims to use electron spin, not just charge, for information processing. This could lead to faster, lower-power devices that combine logic and memory. Let me summarize the scientific workflow we've followed in this lecture. Step 1. Measure resistance as a function of magnetic field and observe the giant magnetoresistance effect that cannot be explained by classical physics. Step 2. Build a baseline classical model without spin-dependent scattering and show that it predicts no magnetoresistance, revealing the inadequacy of the classical picture. Step 3. Use modern thin film deposition to fabricate controlled multilayer nanostructures with atomic precision. Step 4. Systematically measure and compare resistance in parallel versus antiparallel magnetic configurations to quantify the effect. Step 5. Develop a quantum mechanical spin transport model based on Mott's two-current picture and fit it to data to extract parameters like spin asymmetry. Step 6. Validate the model by predicting and confirming how GMR scales with layer thickness, number of layers, and interface quality. What are the key physical insights that make GMR work? First, electron spin is not just an abstract quantum number. It directly affects how electrons scatter and transport through materials. Second, ferromagnetic materials have fundamentally different electronic structures for spin-up and spin-down electrons. The density of states at the Fermi level is highly spin asymmetric. Third, interfaces between materials provide strong spin-dependent scattering. Majority spins transmit easily, minority spins scatter strongly. Fourth, when layers are aligned parallel, majority spin electrons have a clear, low-resistance path through the entire stack. Fifth, when layers are antiparallel, every spin channel encounters high scattering in alternating layers, greatly increasing overall resistance. Why did this discovery merit the Nobel Prize? Let me give you several reasons. First, it beautifully confirmed predictions of quantum mechanics in engineered nanoscale structures. Spin-dependent transport was predicted theoretically, but not clearly demonstrated until GMR. Second, it created an entirely new field of research called Spintronics, with thousands of researchers worldwide now working on spin-based devices. Third, it had immediate and transformative technological impact. Within 10 years of discovery, GMR sensors were in every hard drive, creating economic value in the hundreds of billions of dollars. Fourth, by enabling massive increases in storage density, GMR made possible the mobile computing revolution. Your laptop, smartphone, cloud servers all rely on this technology. Let me close with some thoughts on the pipeline, from fundamental science to transformative technology. GMR is remarkable for the speed of translation. The discovery was published in 1988, and by 1997, IBM had the first commercial GMR hard drives. Only 9 years from fundamental discovery to market. Several factors enabled this speed. The hard drive industry already existed with manufacturing infrastructure. The need for better sensors was clear. And the physics, once understood, was robust and reproducible. Success required deep integration of materials, science, quantum mechanics, and device engineering. No single discipline could have achieved this alone. The broader lesson is that fundamental research on seemingly esoteric topics like spin-dependent scattering in magnetic multilayers can have enormous practical impact that was completely unpredictable at the time. In conclusion, giant magnetoresistance exemplifies how careful experimental observation, rigorous theoretical modeling, and systematic validation can reveal new physics that transforms technology. We've followed the complete scientific workflow from discovery through model building to practical application. This same approach continues to drive advances in spintronics, from TMR to spin transfer torque to topological materials. Thank you for your attention.